Hello, I'm Ankur Mukherjee, and I'll be doing a few basic experiments with a few audio samples. One being my speech, that's pre-recorded at 44.1 kilohertz sampling rate, and the other one being a piano piece by Chopin. It's a nocturne. So let's first see the effects of downsampling and upsampling the piano piece. So this is the one, function F9, and let's play it at the same sampling rate at which it was recorded, 44.1k. Yeah. Now let's downsample this. So down sample x by a factor of say 2. Okay, and let's play this x1, and I'm not changing the sampling rate, and let's see what happens by not changing it. So the piece goes exactly one octave higher, so like the whole frequency range shifts by a factor of 2, and that's because we have reduced the number of samples in x1 because we're downsampling it. You can see it here by the values, like it's like 4 and it becomes 2, it just reduces by half, but we still keep the sampling rate the same, and it plays the record at just one octave higher. So what if we want to make it sound the same, we'll have to reduce the play rate by the same factor, the same downsampling factor. So now let's see. Yeah, so now it sounds the same. So the same applies with the upsampling. Okay, let's upsample. Okay, upsample the piece by a factor of 2, and let's play it at the same thing. In this case, the since we're upsampling it and we are playing it at the same sampling rate, so it should sound one octave lower. Let's see that. Yeah, so that was expected. Now if we want it to sound the same, so we have to multiply this by the same factor. Now this sound, although the octave stays the same as the original one, but there is some noise that's being added, and that's because of the fact that the upsampling actually introduces zeros, interpolates it with zeros. Uh, so let's have a look at the matrix. You see, for every one sample, like every sample becomes like the size increases by a factor of 2, since the coefficient was 2 in here. So for every one sample, it interpolates it with a 0. So that's why we get that sound, we get that noise coming in. Now let's try close this and try the same with my audio, function F9. Okay, it was recorded at the same sample rate at 44. Although we don't have to record audio at 44.1 kilohertz because our voice stays well below 3 kilohertz. So now if we want to satisfy Nyquist, so that should be a sampling rate of 8 kilohertz. But I just recorded it at 44.1, so Let's see.
Hello, I'm Ankur, and this is a test audio.
Yeah, so this is the matrix. Let's see. Mm, let's do a stem. Let's do a stem plot to see how it exactly looks like. Mm, yeah. So this is how it looks like. And to get a better understanding of how distribution is, so let me plot a histogram of my of this sample. So let's say there are 1,000 bins. So yeah, so this is how the distribution of my speech is, and it's localized, highly localized at 0, and it falls off sharply at the edges. So it kind of resembles a Laplacian distribution, and I'll come to that in a minute. So let's see the effects of upsampling it. X1 equals sample x, let's say by a factor of 3. Okay, and see, you can see the numbers 2 becomes 6. So let's see the uh, actually I should stem it because that make much more sense. X1 okay, actually since the factor is 3 here, so for every one sample it puts 2 zeros. So uh, that's like how we had in the last case. For one sample there were 2 zeros, and there was 1 0 because the factor was 2. And let's now sound this at the let's sound x1. Now we are upsampling it, so we must multiply this by the same factor.
Hello, I'm Ankur, and this is a test audio.
Yeah, so again that noise comes in due to the zeros in the zeros in between, like, yeah. So here it is, so it's like one sample and 2 zeros. So that's how MATLAB does the upsampling. It interpolates with zeros. uh, yeah, so this is the upsampling and downsampling, resampling part. Let's now try quantizing it. So this is a MATLAB command that I'm going to use. Y equals x, which is my voice, and should be encode. Okay, max absolute value. I'll just explain the syntax in a minute. Okay, so y is the quantized voice, my voice quantized. Let's have a look at it. So okay, these numbers don't make much sense, but I'll explain the syntax. So here it's a MATLAB inbuilt command. Once again, you encode uh, quantizes my it encodes my voice, that is a sample value, the test audio to 32 levels, uh, 32 levels, and max absolute x being the uh, the I mean the range, like, which we want to divide it into. So this so the inverse operation of this would be to decode it. So let's do that. So yd equals u decode y comma 32 levels, and say max of abs of x So yd was this, and yd and x is like are the same. Let's have a look at it. This is x, and the star values, let's go up. So again zeros, and then so at around 168 we get to see some values. So let's see if it's the same. yd, actually yeah, it appears to be the same, but actually I can just stem the error. So error being yd minus x. So it's very less. So it's like 10 raised to minus 10. So it's insignificant. So this was uniform quantization, but in telephonic systems or in communication systems where we work with human speech, we generally don't um, do a uniform quantization because of certain characteristics of human speech. Like 50% of the time the volume is less than 25% the RMS value of speech. So there's a lot of silence in between, so that's what it is. And 15% of the time the amplitude of the signal actually exceeds its RMS. So that was what we got, right? When the histogram was plotted. Let's plot it again. Hist of x. I need to specify the number of bins, 1000. So again, this is the histogram. You can see it's highly concentrated over here, and it just goes down towards the tail abruptly. So that's why uniform quantization is not done, and this is passed through a compressor. So basically something like a log function. What it basically does is we have a lot of quantization levels at the lower volume parts of the speech, and as the volume goes higher and higher, we represent that by less number of quantization levels, because once the amplitude goes up, we as humans lose the ability to distinguish, perceive noise. So that fact is exploited, and the speech is compressed, and the decompression is done by an expander. So the an expander, a compressor and an expander together is known as a compander. So that's what is done when it comes to human speech, and it's not transmitted as such. Now, instead of 32 levels of quantization, let's try by reducing the number of levels. So let's say we just divide into 8 levels, and yd is again, so we're getting it back. So encoding and then decoding it. And now let's plot the error. So last time when it was like 32 levels, the error was in the order of 10 raised to minus 10, if I'm not wrong. Now this time it increases to 10 power minus 3. So we see a quite significant amount of increase in the quantization error. So this makes sense, because if we increase the quantization levels, we are going to get a near accurate, like more the number of quantization levels, the better the signal is and better it sounds. But we can't just keep increasing the levels because of storage and transmission and stuff. So there's always a trade-off. So all right, thanks for watching.